The oceans comprise about 14,57,000 cubic kilometers of water, that is about 97.2% of the world's total water resources. The ocean is the final repository of debris from the land. The Indian Oceans, with an area of 7,32,46,500 square kilometers, is 1/7 of the Earth's surface and is the smallest of the world oceans. The Indian Ocean is third in size, ranking below the Pacific and Atlantic Sea. Human beings are traditionally used the oceans for transportation and fishing. Transportation and fishing have been the two most important economic activities carried out on the sea oceans. Fishing still continues to be a major source of food for the people. An increasing population and the consequent rise in demand for fuels, metals and construction materials are outstripping the resources available on land. Whatever resources are left, they are either too deep or uneconomical to extract. At the same time, most of the resources available on land are exhausted or nearing exhaustion. These two factors have necessitated the exploration of new resources in the oceans. This trend is more apparent in the case of petroleum natural gas, for which the continental shelf has become a prime source. The new legal regime created by the law of the sea has affected the management and protection of traditional marine resources. The new technologies are being developed to extract the various resources like that oil and gas, minerals and energy resources like coal, etc. At present, the capability to work for a longer period at the bottom of the ocean is extremely restricted, except with the help of expansive specialized devices. Marine minerals can be classified based on the following aspects: based on the region, based on the origin, based on the mode of occurrence. Based on the regions are mainly of two types. One is continental margin, either it may be in the form of continental shelf or may be continental slope or it may be a continental rise. And the second one is the ocean basins. The second is based on the origin. Then based on the origin, the marine minerals can be classified as follows. Terrigenous. The terrigenous marine minerals are originated from the land. After weathering of rocks, the minerals separated from the host rock and transported to the sea. Biogenic. The biogenic marine minerals are derived from organisms. Orthogenic. Orthogenic marine minerals are derived from the precipitation from seawater. Diagenetic. Diagenetic marine minerals are produced by alteration of existing materials. Volcanogenic. Volcanogenic marine minerals are derived from volcanoes. Meteoric. Meteoric marine minerals are derived from the atmosphere. And the third is the mode of occurrence. Used on the mode of occurrences, marine minerals can be classified as follows. One is consolidated and another is unconsolidated. Number 1, consolidated. The consolidated marine minerals are biogenic, example coal, limestone, gas, methane, that is sulfur or sulfate. The orthogenic, the example is cobalt, iron, manganese, platinum, phosphorite, potash, salt like halite, sodium chloride, sulfur, pure and sulfates, etc. Then diagenetic, that is solid layered deposits such as phosphorite. Volcanogenic, the example is lode and vein deposits of massive sulfide deposits like copper, iron, zinc, silver and gold. Unconsolidated materials. The unconsolidated marine mineral resources are terrigenic. The minerals of terrigenous origin can be classified further as metals and non-metals. Metals. Metals of terrigenic origins found in continental margins are as follows. Placer deposits such as heavy minerals and heavy metals concentrates, the barium, that is nothing but the barium witherite, then chromium, that is chromite, gold, iron, hematite, magnetite, siderite, etc. and rare earth elements like monazite and basonite, and tin, the example is cassiterite, then titanium like ilmenite and rutile, then thorium is monazite, then tungsten is scheelite and wolframite, zirconium, that is zircon, etc. Coming to the non-metals of terrigenous origins found in continental margins are as follows: beach deposits such as siliceous sand and gravel, that is nothing but quartz, and placer deposits such as diamond. Marine mineral resources are found either dissolved in the seawater, or they can be found as deposits either on the surface or below the surface. Marine mineral resources are categorized by the dissolved in seawater, surface deposits found as continental shelf slope deposits, and deep sea deposits, and third one is subsurface deposits. Minerals dissolved in seawater. Each cubic kilometers of seawater contains about 165 million tons of solids, making the 350 million cubic kilometers of seawater, that is the world's largest continuous ore body. 64 of the 92 naturally occurring chemical elements are dissolved in the seawater. Sodium and chlorine are the most abundant, accounting for 85% of the sea's dissolved salt. Magnesium, bromium are the other important chemical elements. Minerals of value are gold, silver, zinc, uranium and thorium. It is also estimated that ocean as a whole contains about 6 MMT of gold deposits. Throughout the world, a ton of seawater contains about 60 milligrams of gold. Only magnesium, bromine and common salts are abundant enough to be extracted profitably with present prices and technology. The most of the metals such as copper, zinc, gold and uranium exist in extremely low concentrations. Coming to surface deposits. The surface deposits found on the continental shelf and slope and deep sea deposits. Continental shelf and slope deposits. The deposits found on the continental shelf and slope regions are found mixed with sand containing calcium carbonate, iron, tin, uranium, gold, diamond and platinum, etc. Zircon, monazite and rutile are found along the west coast of India and coastal Brazil, Australia, New Zealand, Sri Lanka and USA. India possesses 90% of the world's monazite reserves in Kerala placer deposits. Rutile is the beach placer deposits is found along the western and eastern coast of Australia. Magnetite occurs in these areas where the volcanic rocks materials are deposited. Such formations are found along the western coastal belts of North America and east coast of Asia in Japan. The reserves of iron rich sediments in Japan is estimated to be 36 million tons. Cassiterite is an important ore of tin, is a residual mineral of the weathering of granites. A belt stretches for about 3000 kilometers from northern Thailand and western Malaysia to Indonesia. Here, the sediments rich in tin have been dragged for hundreds of years and supply more than 1% of the world's market. Gold placers are found to occur along the coast of Alaska, on shelf zone of East Pacific and in river delta sediments along the Oregon, Chile, South Africa and Australia. Diamonds. Diamonds also, like gold, is found in sediments washed down the rivers in some of the areas of Africa and Australia. It is found mixed with sand in a belt running thousands of kilometers away from the southwest African coast. Platinum along the sand is found in parts of United States, Australia and South Africa. Muds bearing copper, zinc, lead and silver also occur on the continent slopes further or too deep for exploitation, considering the present demand and their market value. Coral sands are mined in Fiji, Hawaii and along the US Gulf Coast. sands are mined as a source of calcium. Carbonate throughout the Bahamas island, which has an estimated resource of 100 million metric tons. Sulfur needed for industrial uses, it is known to exist in the Gulf of Mexico and the Mediterranean Sea, where the reserves are to be tune of millions of tons. Coming to deep sea deposits. In these areas, two main types of mineral deposits are economically important. These are the manganese nodules and metalliferous sediments. Both these deposits are related in origin, but are usually found in different areas of the ocean floor. Manganese nodules are the most abundant in the deepest part of the oceans, other than the trench regions. Manganese nodules are found scattered across the world so deep in the red clay regions of the northeastern Pacific, and these nodules were discovered by the Challenger's expedition during 1873 to 1876. In the last 25 years, they have been the focus of intense research and development of mining and extraction techniques by large mining corporations and multinational consortia. Manganese nodules are the most valuable deep sea mineral resources at present. They occur as unconsolidated deposits at the bottom of the ocean. They contain concentrations of valuable metals such as nickel, copper and cobalt, lead and zinc, all precipitate from seawater. The main source of the metals probably are marine exhalates, that is as chlorides, or from the land as hydrated oxides. Metals are leached by hydrothermal circulation along the mid-ocean ridge system and oxidized in contact with the oxygenated bottom water. Manganese nodules grow readily and exhibit a growth of nodules is very slow, being about 0.1 millimeter per 1000 years. The mineral content of the nodules varies from place to place. The nodules contain a detrital matter as indicated by aluminum and some organic structures that once lived attached to the surface of the nodule during its accretion. Because the structure of the nodules is rather spongy, their average density is somewhat lower, making them buoyant. These nodules are developed to the greatest extent in the North Pacific, Indian Oceans and parts of South Pacific Oceans. Coming to the subsurface deposits, the most important of the subsurface deposits are oil and natural gas. These two deposits represent 90% of the mineral value presently taken from the sea. The major offshore oil fields are found in the Gulf of Mexico, the Persian Gulf, the North Sea and off the northern coast of Australia, the southern coast of California and the coasts of African oceans. There are still many areas of the world that are relatively explored in terms of oil and gas. The subsurface deposits are mostly found on the continental shelves, where the conditions for the availability of petroleum are conducive. There are many structures which acts as a trap for petroleum and natural gas. One such structure is called as salt dome, where petroleum and natural gas is trapped in the uplifted and fractured rocks around the dome. In addition to petroleum and salt domes are such resources are sulfur. Sulfur accumulates around the salt plug because insoluble sulfur containing a compound anhydride, that is CaSO4, is generally present in the original salt deposits. Anhydride, which is an altered form of gypsum, is insoluble and forms a cap rock mantle over the salt core. With the help of anaerobic bacteria, anhydride is reduced and hydrogen sulfide gas is liberated, that is H2S gas. Later combines with oxygen dissolved in groundwater to yield sulfur. Sulfur is found off the coast of Thailand and 25 meters deep under oceans. Coal is a byproduct of decomposition of thick lush tropical vegetation and is found on the land surface, but changes in the sea level and land geography over geologic time have caused some coal deposits to become submerged. Submerged coal deposits are found in Japan, UK, Africa and of Mumbai in India. In Japan, under sea coast deposits are reached by shafts that stretch under the sea from a land or descend from artificial highlands. There are three different types of exploration, that is near shore mining for sand and gravel. Lagoon sand and gravel mining is common in many Pacific Islands countries, that is PICS, and has been ongoing for many years. The sourcing of sand and gravel from near shore areas is considered to better option for smaller island countries. A number of dredging methods are commonly used for offshore sand and gravel extraction in the Pacific Islands and some of the regions, including the suction pumps and other drag lines. Most of these aggregates extractions activities have occurred near the shore in protected lagoon at areas less than 15 meters deep. These dragged materials, that is mud, sand and gravel, are used for a range of purposes such as the construction of buildings, roads, seawalls, cement making and land reclamation. Near shore mining for valuable minerals. The interest in offshore diamond mining on the southern African coast, that is Namibia and South Africa, is reported to have gathered a pace in the mid 1900s following the discovery of diamonds in a coastal area of Namibia. 1.5 million carats of diamonds were extracted between 1961 and 1970. However, the low diamond prices and lack of technology led to downscaling marine mining operations in 1970. With the development of appropriate technology, the industry began to take shape again in 1990. Recently, larger scale diamond mining conducted in relatively a deeper continental shelf within and beyond 300 meters water depth with the aid of vacuum pumps. Deep sea mining. Early efforts of developing offshore mining technology were undertaken in the 1970s and 1980s by the multinational consortia composed of governments, private companies and public agencies. Since the early 1990s, a number of developed countries including Germany, Japan, China, Korea, India and the United States were reported to have been working on developing new offshore mining technology. Over the years, a number of these companies have made a significant progress in the development of special mining system for collecting and lifting nodules. Recently, a Nautilus has reported that it is in the process of developing and production system using existing technologies adopted from the offshore oil and gas industry to enable the extraction of high grade seafloor massive sulfide deposits. On a commercial scale, this planned mining system has three major components. One is a mining support vessel, that is MSV. The second is a riser and lifting system, that is RALS, and a seafloor mining tool, that is SMT. Some of the major issues that are likely to impact any mining operations and need to be addressed to are appropriate mining methods that need to used considering the nature of occurrence of these nodules or these minerals. The development of robust mining equipment which can operate at such water depth and environment. Impact of fluctuating prices of minerals commodities on any mining operations. The issues relating to environment management and mitigations of possible environment impacts. Interest in the potential of manganese nodules generated a great deal of resource assessment activity in 1960s and 1970s. The significant resources were invested in identifying the potential deposits and conceptuation of their technology for mining and processing nodules. This was followed by limited trial mining efforts for manganese nodules. Salt domes are largely subsurface geologic structures that consist of a vertical cylinder of salt including halite and other evaporated, etc. A salt dome consists of a core of salt and an envelope of surrounding strata. In some areas, the core may contain a cap rock or sheaths or addition to salt. The size of typical salt domes including cap rock and sheaths are considerably varies from place to place. In most cases, the diameter is a kilometer or more and may range up to more than 10 kilometers. The cores of salt domes of the North American Gulf Coast consists virtually of pure halite, that is nothing but sodium chloride, with minor amounts of anhydrite, that is calcium sulfate, and traces of other mineral layers. Layers of white pure halite are interbedded with layers of black halite and anhydrite. A German salt dome cores contain halite, sylvite and other potash minerals. In Iranian salt domes, halite is mixed with anhydrite and mud, that is nothing but even it mixed with marl, that is nothing but argillaceous limestones and large blocks of limestones and igneous rocks. Distribution of salt domes or distribution of salt structures. Salt structures develop in any sedimentary basin in which thick salt deposits were later covered with thick sedimentary rocks or sedimentary strata or tectonically deformed of both. With the exception of the shield areas, salt structures are widespread. By their very nature, the clastic salt domes generated by gravitational instability alone are limited to the areas that have not been subjected to a significant tectonic stresses. Some salt domes do, however, occur in regions that were subject to a tectonic stress. There are many areas of salt structures in the world or representative of all. These are the Gulf of Mexico, the region of North America, the North German North Sea of Europe and the Iran, Iraq, Arabian Peninsula of Middle East. Economic significance of the salt domes. Salt domes make excellent trap for hydrocarbons because surrounding sedimentary strata are domed upward and blocked off. Major accumulations of oil and natural gas are associated with the domes in the United States, Mexico, the North Sea, the Germany and Romania. In the Gulf coastal plains of Texas and Louisiana, salt domes will be as a significant source of hydrocarbons for some years to come. Huge supplies of oil have been found in salt domes areas off the coast of Louisiana, and some individual salt domes are in the regions of believed to have reserves of more than 5 lakhs barrels of oil. Salt domes in northern Germany have produced oil for many years. Exploration for salt dome oil in the North Sea has extended productions offshore. Then finally the conclusions. The ocean is the final repository of debris from the land. The transportation and fishing have been the two most important economic activities carried out on the oceans. The ocean is the world's largest continuous ore body. Phosphorate, which can be mined to produce phosphate needed for fertilizer industries. Manganese nodules are the most abundant in the deepest part of the ocean. Manganese nodules are most valuable deep sea mineral resources. The most important of the subsurface deposits are oil and natural gas. Salt domes makes excellent trap for hydrocarbons.